Millions of galaxies are hiding a secret. Deep within the constellation Leo, a vast cosmic neighborhood known as the Leo cluster is filled with mysteries that defy everything we think we know. By the end of this journey, you will witness 25 unexplained phenomena that are actively rewriting the rules of physics. We will encounter a phantom ring of light with no clear origin and galaxies that spin in impossible ways. What does it feel like to stare into a cosmic puzzle with no solution in sight? The first mystery is a ghostly loop of light suspended in the void. Known as the Leo ring, it is a colossal, faint circle of hydrogen gas and young stars that wraps around two giant galaxies, M105 and NGC 3384, like a cosmic lasso. Its discovery came not from visible light, but from the silent whispers of radio telescopes, revealing a structure so vast it defies easy explanation. Picture, if you will, a ring of star-forming material nearly 650,000 light-years across, a fragile, filamentary halo that should not, by our current understanding, be able to hold itself together so gracefully. It is a cosmic artifact with no clear origin story. One leading theory suggests it is a primordial remnant, a leftover strand of gas from the very formation of the universe itself, a fossilized thread that never coalesced into a proper galaxy. Another, more dramatic idea paints a picture of an ancient, slow-motion collision, a titanic gravitational tug of war between the two galaxies that pulled a river of gas out into this immense, stable ring. Yet neither theory fully satisfies the questions. How does this delicate structure maintain its coherent shape over billions of years? Why does it host pockets of young, blue stars, indicating ongoing, if sporadic, creation within a cloud of gas that seems too diffuse to collapse? The Leo ring glows with the soft, haunting light of a mystery that predates our solar system, a phantom signature in the dark that challenges the very narrative of how cosmic structures are born and endure. This faint ghost of a galaxy presents a different kind of puzzle, one of profound absence. Drifting silently within the Leo cluster is an object that defies every expectation of size and substance. It is classified as an ultra-diffuse galaxy, a cosmic paradox. This galaxy, known to astronomers by a catalog number, spans a diameter comparable to our own majestic Milky Way. Yet, where the Milky Way blazes with the light of hundreds of billions of stars, this phantom holds barely 1% of that number. Its stars are so few and far between that the galaxy is almost transparent, a wispy, ethereal smudge against the dark. Its very existence here, in the violent heart of a dense cluster, is a direct challenge to our theories. Think of the Leo cluster as a crowded, chaotic city square, with galaxies constantly brushing past each other, their immense gravitational fields pulling and distorting everything nearby. According to our models, a structure as fragile and sparse as this ultra-diffuse galaxy should have been shredded to pieces by now, its scant stars scattered by these relentless gravitational tides. That it remains intact is the first layer of the mystery. So what is it? Astronomers are locked in a debate between two compelling yet troubling ideas. Is this a failed galaxy, a cosmic underachiever that formed from a cloud of gas that was somehow too serene, too quiet, to birth more than a handful of stars? Or is it the ghost of a once normal galaxy that had the terrible misfortune of wandering too close to the cluster's center, having nearly all of its star-forming gas and countless stars violently stripped away, leaving only this faint skeleton behind? Observations deepen the enigma. The motions of its few remaining stars suggest this ghostly object is held together by an immense, unseen anchor, a halo of dark matter that is surprisingly massive and dense. This invisible scaffold appears to be the only thing preventing the galaxy from dissolving into the void. So we are left with a specter as large as our home, but almost empty, surviving against all odds in a dangerous neighborhood and seemingly built upon a hidden foundation of darkness. It is a monument to everything we do not yet understand about how galaxies live and die. But the Phantom Galaxy is not the only place where dark matter seems to be playing by its own rules. This brings us to a deeper, more fundamental puzzle, the mysterious dark matter halo discrepancy. For decades, the prevailing model of the universe, known as lambda CDM, has rested on a simple, powerful idea. Every galaxy, especially massive ones in dense clusters, should be embedded within a vast, heavy cloak of invisible dark matter. This dark matter halo is the gravitational anchor, the unseen hand that dictates how fast stars should orbit the galaxy's center. We can predict these speeds based on the visible mass we see, the stars and gas. The prediction is a specific curve, a graph that shows how orbital velocity should drop off sharply as you move from the bright core out into the sparse outskirts. Yet, when astronomers point their most powerful telescopes at certain galaxies within the Leo cluster and measure the actual speeds of stars and gas clouds, they find something astonishing. The velocity curve does not fall. It stays flat or sometimes even rises slightly all the way out to the galactic frontier. This flat rotation curve is the classic signature of dark matter, proof of an immense unseen mass exerting its pull. But here is the twist. For a handful of galaxies in Leo, the measurements tell a different story. Their rotation curves do fall, just as the visible mass alone would predict. It is as if the dark matter cloak, which should be thick and heavy, is startlingly thin or even missing altogether. One prominent example is the galaxy known as NGC 3368. Based on its size and location in the cluster, models suggest it should possess a dark matter halo dozens of times more massive than its stars. Yet the meticulous tracking of its stellar motions reveals a gravitational profile that can be almost entirely explained by the luminous matter we can see. This is not a minor accounting error, it is a direct contradiction. If our standard model is correct, these galaxies should not exist in their current form. They should fly apart. The fact that they hold together, seemingly without their prescribed allotment of dark matter, sends shockwaves through cosmology. It forces a difficult question. Are we looking at galaxies that had their dark matter stripped away by violent encounters within the cluster, a process we do not fully understand? Or more radically, does this discrepancy point to a flaw in our fundamental understanding of gravity itself? This is where theories like modified Newtonian dynamics, or MOND, enter the fray. MOND proposes that on the vast, gentle scales of galaxies, gravity behaves differently than Newton or Einstein described. It suggests a slight modification to the laws of physics that could make galaxies behave as they do without requiring any invisible dark matter at all. The flat rotation curves of most galaxies were the primary evidence that led to the dark matter hypothesis. Now, the few galaxies with falling curves in Leo have become the primary evidence for those challenging it. The controversy is fierce and ongoing. Every new observation is scrutinized, every measurement double-checked. Is this a clue to new, exotic dark matter particles that interact in unexpected ways? Or is it a sign that our theory of gravity, the very framework of the cosmos, needs a rewrite? The Leo cluster is not just a collection of galaxies, it is a cosmic courtroom, and these anomalous galaxies are presenting evidence that could change everything. The invisible structure of the Leo cluster holds another startling secret, one written not in starlight, but in the searing heat of a million-degree gas bath. This hot, thin plasma fills the space between galaxies, glowing fiercely in the high-energy language of X-rays. When astronomers first mapped this glow with telescopes like Chandra, they expected a smooth, simmering fog. What they found instead was a cosmic Swiss cheese. Embedded deep within this luminous gas are immense, perfectly defined cavities, vast bubbles of near-nothingness that stretch for tens of thousands of light-years. They appear as dark voids in the false-color X-ray images, like ghostly footprints pressed into an incandescent mist. These are the X-ray cavities, and they are the scars of a titanic struggle between creation and destruction. The leading explanation points to the supermassive black hole at the heart of the cluster's central galaxy. We think of black holes as ultimate consumers, but they can also be phenomenal engines. As matter spirals into the abyss, not all of it crosses the event horizon. Some is channeled and accelerated into opposing jets of particles and magnetic fields, spewing out at nearly the speed of light. These jets act like cosmic blowtorches, plowing into the surrounding hot gas and inflating gigantic, bubble-like cavities. The process is akin to blowing a bubble in a thick liquid, where the jet's energy pushes the multimillion-degree plasma aside, creating a relatively empty pocket. But the scale here is almost incomprehensible. The energy required to carve out these voids is staggering, equivalent to the simultaneous explosion of billions of supernovae. This suggests the central black hole experienced eruptions of almost unimaginable violence in the relatively recent cosmic past. What could have triggered such a catastrophic feeding frenzy? Did a whole galaxy wander too close and get torn apart, funneling a sudden, vast river of stars and gas into the black hole's maw? Or is this the signature of a more cyclical, pulsing instability inherent to these monster engines? The mystery deepens when we consider the cavity's pristine shapes. In a turbulent, dense environment like a galaxy cluster, such clean, coherent structures should not last. The superheated gas should rush back in, the bubble should wobble, distort, and dissipate within a few 100 million years. Yet these cavities remain distinct and symmetrical, as if the eruption happened yesterday. This implies they are either being actively re-energized by ongoing, quieter jet activity, or they are somehow buoyant, floating upward through the cluster gas like hot air balloons, maintaining their form against all odds. These ghostly X-ray bubbles are therefore a frozen moment of extreme violence, a testament to a black hole's power to reshape its entire universe on a colossal scale, while posing a quiet, persistent question about how such delicate imprints of fury can endure for eons. The silent testimony of stellar motion often holds the most damning evidence. Far from the cluster's chaotic core on the quieter outskirts, the spiral galaxy NGC 3521 spins with a secret. Its graceful arms, traced by billions of stars, should obey a simple gravitational rule. The speed of a star's orbit depends on the mass pulling it inward. Since most of a galaxy's visible mass, its stars and gas, is concentrated in the bright central bulge, we expect stars in the outer reaches to orbit more slowly, like distant planets in a solar system. For NGC 3521, detailed kinematic maps, which chart the precise velocity of stars and gas across every part of the disk, reveal something profoundly different. The outer regions of this spiral do not slow down. They race around the galactic center at speeds that are far too high, and they do so with a surprising degree of coherence, as if the entire outer disk is a single, rigid plate. This flat, high rotation curve is the classic signature of dark matter's gravitational grip. But here, the puzzle takes a peculiar shape. The amount of unseen mass required to explain this motion does not match the standard, smooth halo of dark matter our models predict. Instead, it suggests a hidden reservoir of mass with a bizarre, lopsided distribution, perhaps concentrated in the galaxy's outer disk or in a vast, unseen stream wrapping around it. This anomaly forces astronomers to consider uncomfortable possibilities. Is NGC 321 interacting with a companion galaxy or a dark matter sub-halo we simply cannot see, a gravitational tug warping its motion from the shadows? Or does this precise measurement point toward a more fundamental crack in the dark matter paradigm itself? NGC 3521 is not alone. Other spirals, both within Leo and beyond, show similar kinematic surprises where the outer stars move in ways that are difficult to reconcile with a simple, spherical dark matter cloak. Each one is a data point in a growing rebellion, a suggestion that our map of the invisible universe may be incomplete, or that the laws governing galactic dance floors need a subtle but critical revision. The serene rotation of a distant spiral galaxy thus becomes a silent revolution, its stars tracing out a question mark in the void. The violence of the Leo cluster's past is etched across the heavens in a form of light invisible to our eyes. On the very fringes of this galactic gathering, radio telescopes have captured the ghostly outline of a cosmic tsunami. It is a colossal, crescent-shaped structure known as a radio relic, a fossilized shock wave of staggering proportions. This faint arc of radio emission stretches for millions of light years, a silent testament to a cataclysm of almost unimaginable force that occurred when the universe was half its current age. The leading theory paints a dramatic picture. We believe this relic marks the site where the Leo cluster itself violently merged with another, smaller cluster of galaxies billions of years ago. Think of it as the aftermath of two immense crowds of galaxies and dark matter smashing together at speeds of thousands of kilometers per second. The collision would have sent a titanic shock wave, like a sonic boom on a universal scale, racing out through the thin, magnetized gas that fills the space between the clusters. This shock wave, traveling faster than the speed of sound in that plasma, acts as a natural particle accelerator. It sweeps up electrons and hurls them to velocities approaching the speed of light. When these ultra-relativistic electrons spiral along the shock's magnetic field lines, they emit the faint radio glow we detect as the relic. It is a cosmic signpost pointing directly to the epicenter of an ancient disaster. Yet, the closer astronomers look, the more enigmatic this relic becomes. Its properties push the limits of our physics. The magnetic fields within the shock appear to be incredibly strong and ordered, far more than our simulations of such mergers predict. Furthermore, the mechanism that accelerates particles to such phenomenal energies within the shock is not fully understood. Standard models struggle to explain how the shock wave can be so efficient, turning the chaotic energy of a collision into such a coherent and powerful radio beacon. Some scientists propose that pre-existing turbulent magnetic fields in the region were amplified to extreme levels by the passing shock. Others wonder if there is a more exotic process at work, perhaps involving the shock wave re-accelerating a sea of old, leftover electrons from earlier cosmic events. The relic is not just a scar, it is a living puzzle. By studying its detailed structure and spectrum, astronomers are essentially performing forensics on a crime scene billions of years old. They can estimate the speed and angle of the ancient collision, gauge the strength of primordial magnetic fields, and test the limits of how the universe transforms raw violence into radiant light. But the precise story of this merger, the identity of the victim cluster, and the exact chain of events that sculpted this perfect arc remain locked within the relic's faint radio whisper. It is a frozen moment of cosmic chaos, a reminder that the quiet clusters we see today were forged in fires of unbelievable fury, whose echoes still reverberate across the void. Our models of cosmic construction face a quiet but profound crisis in the Leo cluster. According to the most sophisticated computer simulations of our universe, a giant galaxy like the ones at the cluster's heart should be surrounded by a bustling swarm of hundreds of smaller dwarf galaxies. These dwarfs are the cosmic building blocks, the leftover fragments from the assembly of the giants, and they should be held in orbit by the immense dark matter halo. The prediction is clear and robust. Yet, when astronomers point their most powerful telescopes toward the Leo cluster and conduct painstaking, ultra-deep surveys, they count only a few dozen. The vast majority of this predicted dwarf galaxy population is simply missing. This is not just a minor shortfall, it is a glaring discrepancy known as the missing satellite problem, and in the dense, ancient environment of Leo, it feels especially acute. Where did all those dwarf galaxies go? One possibility is that they are there, but hiding in plain sight. Perhaps they formed so few stars that they are essentially dark, invisible to our optical telescopes, composed almost entirely of that mysterious dark matter. Searches for these ultra-faint dwarfs continue, scanning for the faintest smudges of starlight or the subtle gravitational wobbles they might induce. Another, more violent explanation is that the cluster itself is a dangerous place. Over billions of years, the relentless gravitational tides from passing giants could have stretched, shredded, and dissolved these fragile dwarfs long ago, turning them into faint stellar streams lost in the background glow. Yet, even this destructive scenario has its limits. Our simulations of such processes still suggest we should see more survivors than we do. This persistent absence forces a more uncomfortable line of inquiry. Could it be that our understanding of dark matter itself is flawed? The standard model assumes dark matter is cold and collisionless, which allows it to clump easily into many small halos that should host dwarf galaxies. If dark matter were slightly warmer or interacted with itself in subtle ways, it might not form as many small clumps, naturally explaining the shortage. Or perhaps the problem lies in the complex physics of star formation in the early universe. Maybe the conditions in those small dark matter halos simply prevented gas from cooling and collapsing into stars, leaving them permanently dark and undetectable to our current methods. Every deep field image of the cluster that reveals empty space where dozens of dwarfs should be glowing is a direct challenge. It tells us that the story of how galaxies gather their satellites, a story we thought we understood, has missing chapters. The silence from the expected swarm of dwarfs is a loud reminder that the universe's history is written in shadows we are still learning to read. The destructive forces within the cluster can sometimes spark creation in the most unexpected places. This brings us to the paradox of ram pressure-stripped galaxies, a process that should strangle star formation but instead sometimes lights a fire. Within the crowded Leo cluster, galaxies are not moving through empty space. They are plunging at incredible speeds through the superheated, thin plasma known as the intracluster medium. For a spiral galaxy rich with cold gas, this is like driving a convertible into a hurricane. The immense pressure of this oncoming wind, called ram pressure, acts as a cosmic sandblaster, violently stripping away the galaxy's star-forming fuel. The result is often a tortured, comet-like appearance with a bright head of surviving stars and a long, faint tail of displaced gas streaming behind. Logic dictates this should be a death sentence for new stars. The galaxy is losing its primary ingredient, yet the universe delights in contradiction. Observations from telescopes like Hubble reveal that within these very tales of grief, vibrant stellar nurseries can ignite. The displaced gas, once torn from the safety of the galactic disk, does not simply dissipate. Under the right conditions, the immense turbulence and compression within the tail can trigger the gas to collapse into dense, luminous knots. These are not just wisps of hydrogen, they are factories for new suns. One stunning example is a galaxy often studied in such clusters, showcasing a brilliant blue tail speckled with the fierce light of young, massive stars. It is a scene of simultaneous destruction and birth. The process forces a radical rethink. We long believed star formation required the serene, stable environments of a galactic disk. Here we see it flourishing in the chaos of a galactic wreck, in gas that is being actively lost to the void. How can this happen? Astronomers theorize that the ram pressure itself, while stripping gas globally, can also pile it up locally. As the wind blows, it can compress pockets of gas to critical densities, seeding their collapse. Alternatively, the sheer violence of the stripping might trigger shock waves within the tail, stirring the gas and prompting it to coalesce. Each bright knot in those Hubble images is a defiance of expectations, a stellar rebellion born from the very forces trying to erase it. These galaxies are cosmic phoenixes, not rising from ashes but creating new fire as they fall. The very heart of the Leo cluster holds a thermodynamic puzzle that defies our most basic expectations of cosmic behavior. Deep in its central region, the intracluster gas is incredibly dense, packed with particles in such close proximity that they should be colliding constantly. According to the simple laws of physics, this constant interaction should cause the gas to radiate away its heat at a ferocious rate, cooling down rapidly. As it cools, this dense gas should then condense under its own gravity, collapsing into a torrential rain of new stars directly onto the central galaxy. Astronomers call this predicted deluge a cooling flow, and for decades they expected to see it happening in every massive cluster. Yet, when they look at the Leo cluster's core with X-ray telescopes, they find a scene of eerie quiet. The gas is indeed cooler than its surroundings, a so-called cool core, but it is not cold enough. That furious, runaway cooling and the resulting firestorm of star formation are conspicuously absent. It is as if you placed a boiling pot in a freezer, but the water refuses to freeze. This is the famous cooling flow problem, and its solution points to a delicate, cosmic balancing act of astonishing precision. The leading theory involves the supermassive black hole at the cluster's very center. We believe it acts as a cosmic thermostat. When the dense gas begins to cool and drift inward, some of it inevitably feeds the black hole. This meal does not go quietly. The black hole responds by powering up its colossal jets, flooding the surrounding region with energy and heat. This outburst stirs up the cooling gas, reheating it and shutting down the very star formation that the cooling was supposed to fuel. It is a perfect, self-regulating feedback loop. The mystery lies in its impossible perfection. How does this process achieve such a fine balance? The energy injected by the jets is neither too weak, which would allow the cooling flood, nor too strong, which would blast all the gas away and destroy the cool core entirely. Instead, it maintains a gentle simmer that has lasted for billions of years. The mechanisms behind this precision are maddeningly complex. Does the black hole pulse in regular bursts like a geyser, or provide a steady, gentle warmth? How does the energy dissipate so evenly through the gas? Current simulations struggle to recreate this stable equilibrium, suggesting we are missing a crucial piece of the physics. Understanding this puzzle is not just academic. The cool core's stability dictates the entire life cycle of the cluster's central galaxy, controlling whether it becomes a bloated, star-forming monster or a quiescent, red and dead giant. It is a masterclass in cosmic regulation, a hidden dialogue between a gravitational abyss and a sea of hot gas, conducted with a silence that speaks volumes about the forces we have yet to comprehend. The perfect silence of the cosmos is sometimes broken by a scream. In 2018, radio telescopes around the world registered a sudden, violent spike in their data. Lasting less than the blink of an eye, a fast radio burst erupted from the direction of the Leo cluster. This millisecond-long flash packed more energy than our sun emits in 80 years, all focused into a single, coherent beam of radio waves. Of the hundreds of these bursts detected, what makes this one so tantalizing is its apparent address. Careful analysis of how the signal was slightly smeared by intervening electrons pointed its origin not to a random point in deep space, but to a specific galaxy within the dense Leo cluster itself. This changes everything. Fast radio bursts are profound mysteries wherever they occur, often attributed to cataclysmic events like the collision of ultra-dense neutron stars or eruptions from highly magnetized stellar corpses called magnetars. But for a burst to come from within a galaxy cluster adds staggering new layers of complexity. The signal did not travel through empty space. It had to punch its way through the cluster's own turbulent atmosphere, that sea of million-degree plasma and tangled magnetic fields we have already discussed. This environment should have left a distinct fingerprint on the burst, twisting its polarization or scattering its waves in measurable ways. The data, however, shows alterations that are subtle and strange, not quite matching our predictions for how the intracluster medium should behave. It is as if the cluster itself is an invisible lens, warping the message in ways we cannot yet decode. the hunt for answers became frantic. Astronomers immediately pointed every available instrument back at that patch of sky, listening for a repeat performance and searching for any lingering glow in optical, X-ray, or gamma-ray light. A repeating burst would be a gold mine, confirming the location and allowing us to study the source's neighborhood. A flash of light from merging stars would have painted a clear picture of the cause. But the Leo cluster burst offered only silence afterwards. It remains a one-off enigma, a cosmic shout with no echo. This singular event forces a difficult question. Was it indeed a spectacular, final death cry from a one-time event like a stellar merger? Or does its origin in the extreme environment of a cluster hint at a completely different engine, perhaps one powered by the unique conditions near a supermassive black hole or within the wreckage of a ram pressure-stripped galaxy? The burst's fleeting passage is a ghost in the machine, a reminder that the most violent events in the universe can be transient and cruel, leaving behind only a scrambled signal and a deepening mystery. Gravity itself can become a lens, bending the fabric of space to show us what our eyes cannot see. Within the Leo cluster, astronomers have found a spectacular example of this cosmic trickery, a gravitational lens where a massive foreground galaxy distorts the light from a more distant object behind it. The result is a stunning arc, a partial Einstein ring, where the background galaxy is stretched and magnified into a luminous crescent. This phenomenon is more than a beautiful illusion, it is a precision scale for weighing the unseen. By meticulously measuring the exact shape and distortion of these arcs, scientists can reconstruct a detailed map of the total mass in the foreground galaxy, including its immense cloak of dark matter. Yet, in the Leo cluster, these cosmic scales are giving readings that do not quite add up. The map of mass inferred from the gravitational lens does not perfectly align with the map of mass we get from adding up all the visible stars and the hot X-ray gas. There are subtle discrepancies, areas where the lensing effect is stronger or weaker than it should be. This points to a hidden landscape within the dark matter halo itself. The leading explanation is that the smooth halo is not smooth at all. It is likely littered with invisible clumps and subhalos, dense knots of dark matter that formed early in the universe and were never incorporated into stars. These unseen substructures act like hidden weights on the cosmic scale, subtly altering the lens's distortion in ways that match the anomalies. Finding them through lensing is one of our most promising ways to probe the very nature of dark matter particles, as their abundance and size depend on whether dark matter is cold, warm, or interacts with itself. But the plot thickens. In some cases, the lensing data reveals not extra clumps, but puzzling gaps or concentrations that are difficult to reconcile with any standard model. Could these mismatches be hints of something more exotic? Perhaps they are signs of dynamical friction, where these dark matter clumps are being dragged and disrupted as they orbit. Or maybe they indicate a property of dark matter we have not yet considered, like a tiny but measurable interaction force between particles. The painstaking work continues, pixel by pixel, as astronomers use the bent light from a distant galaxy to chart the invisible architecture of a closer one. Every anomalous arc is a clue, a silent testament to the fact that even our most powerful tools for mapping the dark universe are revealing a structure far more complex and mysterious than we ever imagined. Deep within the faint smudge of a dwarf galaxy in the Leo cluster, a pinpoint of light screams in X-rays. This is an ultra-luminous X-ray source, a ULX, and it is breaking the rules of cosmic consumption. From a region no larger than our solar system, this object pours out more X-ray energy than 1 million suns emit across all wavelengths. Such staggering power should be impossible for its suspected identity, a stellar mass black hole or a neutron star, the collapsed core of a dead star. The problem is a fundamental limit called the Eddington luminosity. Think of it as a cosmic speed limit for eating. As material falls onto a compact object, the intense radiation it produces pushes back on the incoming matter. There is a precise balance, a point where the outward push of light equals the inward pull of gravity. Exceed that limit, and the radiation should blow the entire feast apart, shutting down the process. Yet this ULX and others like it are operating far beyond that theoretical boundary. They are somehow feeding at super Eddington rates, gorging themselves without being choked off by their own brilliance. How astronomers envision a scenario where the infalling gas does not come in evenly from all directions. Instead, it might form a thick, dense disk with powerful magnetic fields funneling material onto the magnetic poles of a neutron star like a cosmic fire hose. Or for a black hole, the accretion disk itself might puff up into a bloated, donut-like structure that traps the intense radiation, allowing more matter to slip quietly over the event horizon before the light can escape to push it away. It is a precarious, violent balancing act, a testament to physics operating at its most extreme. Finding this particular ULX in a small, low metallicity dwarf galaxy within the Leo cluster adds another layer of strangeness. Low metallicity means this galaxy is poor in elements heavier than hydrogen and helium, a relic of an earlier, purer time in the universe. In such an environment, massive stars are thought to evolve differently, often collapsing directly into black holes with little fanfare. The presence of a ULX here suggests that a binary system survived the death of one star, and that the resulting black hole or neutron star is now voraciously stripping material from its companion. But the cluster environment is a dangerous place for such a delicate, tight binary dance. The gravitational tides from passing galaxies should have disrupted it long ago. That it persists shining with impossible fury forces us to reconsider the life cycles of stars in these ancient, pristine dwarfs and the stability of the binary systems they leave behind. This tiny, brilliant pinprick is a microcosm of cosmic violence, a challenge to the speed limits of physics, shining from a galactic backwater where it has no right to exist. This cosmic defiance of the life cycle is written in a faint, forbidden color of blue. Among the ancient red giants that dominate the Leo cluster's core, there is a massive elliptical galaxy that should be the ultimate cosmic retirement home. Classified as red and dead, its vast population of old, cool stars gives it a uniform crimson hue in standard optical images, a sign that its star-forming days ended billions of years ago. According to the textbook, this is the final, quiet state for a galaxy in such a dense environment. Its cold gas long since evaporated or stripped away by violent encounters. But the universe rarely reads the textbooks. When astronomers trained their most sensitive instruments on this seemingly dormant giant, they saw something impossible. Wrapped around its core like ghostly veins were faint, delicate filaments glowing with a distinct cold blue light. This is the signature of young, massive stars. Furthermore, radio telescopes detected the unmistakable whisper of pockets of cold molecular hydrogen gas, the raw fuel for star birth, drifting within the galaxy's halo. The presence of both fuel and fire in a corpse is a profound contradiction. Where did this cold gas come from in a region sterilized by the cluster's hot plasma? One possibility is a quiet act of cosmic theft. As the giant galaxy moves through the cluster, it could be slowly accreting cool gas from faint streams or even stripping it from a smaller, gas-rich companion during a gentle gravitational encounter, a process too subtle to create the dramatic tales we see elsewhere. Another, more internal theory suggests the gas could be a remnant, cooling out of the galaxy's own halo of hot gas in a slow, dripping process that never quite reaches the critical density for a major burst. This leads to the second layer of the mystery. Why only a whimper with cold gas present? We would expect a renaissance of star formation, a blue blaze of new suns. Instead, we see only these faint filaments, a sporadic sputtering of creation. The answer may lie in the galaxy's extreme environment, the ambient pressure from the surrounding intracluster medium, or even the gentle heating from the galaxy's own supermassive black hole, might be keeping the gas just above the temperature threshold for collapse. It is a state of perpetual frustration where the ingredients for a stellar feast are present, but the kitchen is just too warm to cook. This galaxy, caught between red death and blue birth, shatters the simple narrative of galactic evolution. It proves that the transition from vibrant spiral to quiescent elliptical is not a clean, one-way street, but a complex, messy process with fits and starts, where even the oldest giants can cling to a whisper of youth, defying their own epitaphs with a faint, stubborn glow. The chemical history of the universe is written in that superheated plasma. When astronomers use X-ray telescopes to perform a kind of cosmic spectroscopy on the Leo cluster's intracluster gas, they are reading its elemental composition. They expect to find the heavy elements, the metals forged in the hearts of stars and scattered by supernova explosions, evenly mixed throughout this vast ocean after billions of years of galactic motion and titanic mergers. The reality is a map of bewildering inconsistency. Certain regions glow with a surprising abundance of iron and silicon, while other, equally vast volumes of gas remain relatively pristine, poor in these heavy elements. It is as if someone stirred a cup of coffee, but the sugar settled in strange, isolated clumps. This anomalous metal distribution is a direct challenge to our understanding of how galaxy clusters evolve. These metals are the ashes of dead stars. They should have been blown out of individual galaxies by supernova winds or active black holes, then churned and dispersed by the immense turbulence of cluster mergers until the entire medium reached a uniform, well-mixed state. The fact that we see sharp gradients and pockets of enrichment means this mixing process is either far less efficient than we thought, or something is actively working against it. One theory suggests we are seeing the incomplete digestion of a recent metal-rich meal. Perhaps a single gas-rich galaxy, undergoing a ferocious burst of supernova, injected a concentrated plume of heavy elements into the cluster relatively recently, and there simply has not been enough time for it to spread. Another idea points to the complex physics of the gas itself. The hot plasma is not a simple fluid. It is magnetized and layered with subtle temperature and density differences. These conditions could allow enriched bubbles to remain buoyant, floating like oily slicks on water without fully mixing. Or perhaps the transport mechanisms, like galactic winds or AGN jets, are surprisingly selective, depositing their metallic cargo in specific locations rather than broadcasting it widely. Each explanation has its flaws. A recent injection event should leave other traces, like a disturbed galaxy or shock fronts that we do not always see. Buoyancy and magnetic fields are difficult to model at these scales, and their long-term effects remain uncertain. The clumpy metallicity map thus stands as a stubborn puzzle. It tells us the cluster has a memory, that the chemical legacy of stellar deaths is not easily erased, and that the quiet, hot bath between galaxies is a far more structured and historically complex place than it appears. We are left reading a scrambled recipe where the ingredients of cosmic creation are piled in unexpected heaps, refusing to blend into a smooth, predictable soup. But the cluster's chemical chaos is not the only place where something is missing. A different kind of absence haunts the radio data. There, astronomers have mapped a faint, swirling cloud of atomic hydrogen gas drifting through the cluster's gravity like a phantom. This cloud, detected by its specific radio wavelength emission, contains enough raw material to build a small galaxy's worth of stars. Yet, when they point the most powerful optical telescopes at that exact same patch of sky, they see only darkness. No faint smudge of starlight, no distant glitter of a dwarf galaxy's population. The deep field image reveals an empty spot where the radio map shows a swirling mass of potential. This is a candidate dark galaxy, an object composed almost entirely of gas and presumably the dark matter needed to hold it together. The very idea is thrilling and contentious. Could this be a pristine fragment of the early universe, a dark matter halo that somehow gathered gas but never sparked the fire of star formation? It would be a cosmic fossil in its purest form, a direct window into the conditions before the first stars ignited. Or is the explanation more mundane but no less strange? This gaseous cloud could be tidal debris, a long streamer of gas ripped from a larger galaxy during a past encounter, now stretched and isolated, its stars left behind or never formed in the first place. Follow-up observations have intensified the mystery. Teams have searched for the faintest possible glow of stars, for any trace of ionized gas, or for the subtle gravitational lensing effects that would betray a concentrated mass of dark matter. The results are stubbornly inconclusive. The object refuses to reveal its true nature. This leaves us with a profound question hanging in the void. Are we looking at a true dark galaxy, a landmark discovery that confirms dark matter halos can exist without stars? Or is it a cosmic mirage, a ghost of a past collision that merely mimics what we hope to find? The eerie emptiness on the optical image, superimposed with the clear hydrogen contour on the radio map, creates a cognitive dissonance. We see the evidence of something massive, we see the fuel for creation, but we see no creation itself. It is a silhouette without a body, a promise of a galaxy that never was. The ghostly cool core of the Leo cluster presents a thermodynamic puzzle, but its solution hinges on another, more profound mystery. At the very heart of the cluster's dominant galaxy, where the dense gas should be raining down, sits a supermassive black hole of staggering mass, and it is almost completely silent. This is deeply strange. In other massive clusters, the central black hole is a roaring engine, its powerful jets acting as the cosmic thermostat that prevents a cooling catastrophe. Here, the abundant fuel of the cool core swirls all around it, a lavish feast laid out for a gravitational monster, yet the black hole seems to be barely nibbling. Multi-wavelength observations tell the same quiet story. Where we would expect to see brilliant X-ray flares or the twin lances of radio jets carving through the gas, we find only a faint, sleepy glow. The black hole is quiescent, a sleeping giant in a pantry full of food. So what is suppressing its appetite? One compelling idea is a process called chaotic cold accretion. This theory suggests the infalling gas does not come in a smooth, steady stream. Instead, it condenses out of the hot halo in cold, dense clouds and filaments. These clouds rain down in a chaotic downpour, but they might be so clumpy and turbulent that they largely miss the black hole's direct grasp, falling around it instead of into it. It is like trying to fill a thin straw during a hailstorm. Most of the material just bounces away. Another possibility involves the very magnetic fields that thread the hot gas. These fields could be acting like a cage, providing enough pressure and structure to support the gas and prevent it from funneling efficiently toward the event horizon. The black hole might be starved not by a lack of food, but because the dinner table is magnetically locked. This unusual quiet is not a minor detail, it is the central piece of the unsolved cooling flow puzzle. The black hole's silence means the primary heating mechanism for the entire cluster core is switched off or stuck on low, yet the gas is not cooling uncontrollably either. This implies a state of exquisite, precarious balance achieved through means we do not fully grasp. Perhaps the black hole operates in rare, powerful bursts spaced far apart, cleaning up just enough gas to maintain equilibrium for eons before napping again. Or maybe other, subtler processes, like the gentle stirring of gas by orbiting galaxies, are providing just enough heat to compensate. The unnerving quiet of this colossal black hole forces us to reconsider the relationship between a monster and its environment. It proves that the most powerful objects in the universe can exist in a state of profound restraint, and that this restraint itself may be the key to understanding the delicate, simmering stability of an entire galactic metropolis. Winding through the darkness between the brilliant galaxies is a ghostly river of stars. This stellar stream is a faint, elongated ribbon of ancient suns, stretched across the cluster by gravity's relentless pull. It is the corpse of a much smaller system, a dwarf galaxy or a massive globular cluster that wandered too close to a more powerful neighbor billions of years ago. The gravitational tides acted like a cosmic rack, slowly pulling the victim apart until its stars were strewn across a vast orbit, a glittering scar marking an ancient act of cannibalism. Such streams are common in our own Milky Way, but finding one in the dense, chaotic environment of the Leo cluster is a rare and precious clue. By mapping the precise path and motion of these stars, astronomers can perform stellar archaeology, reading this fossilized trail backwards in time to reconstruct the crime. The chemical fingerprint of the stars, their specific mix of heavy elements, could tell us about the type of galaxy they came from, whether it was a pristine dwarf or a more evolved system. Yet, this particular stream holds its secrets tightly. The forensic investigation has hit a wall. When scientists trace the stream's orbit backwards, the path does not lead conclusively to any of the massive galaxies we see today. It is a trail that seems to vanish into the cluster's messy history. This presents a haunting possibility. The galaxy that destroyed this stream, the culprit in this cosmic murder, may itself be gone. Perhaps it was a mid-sized galaxy that later merged with one of the current giants, losing its own identity in the process. Or, in the violent chaos of the cluster's youth, the destroyer could have been torn apart by an even larger predator, leaving two victims instead of one. Visualizing this requires painstaking work. Teams use ground-based telescopes with ultra-sensitive cameras to take deep, wide-field images of the cluster, filtering out the brilliant foreground galaxies to amplify the faint, smooth glow of the stream. In enhanced views, it appears as a delicate, pale blue arc, a brushstroke of lost light against the black. Animations can then bring the tragedy to life, showing a compact, shimmering dwarf galaxy approaching a looming giant. Over millions of frames compressed into seconds, we watch as the smaller system is stretched, its stars pulled out into a long, shimmering thread that slowly disperses into the void. This ghostly river is more than a remnant, it is a lost chapter. Its unresolved origin means a piece of the cluster's family tree is missing, a progenitor we cannot name and a destroyer we cannot identify. It is a beautiful, haunting reminder that in the cosmos, even the evidence of destruction can itself be erased by time, leaving only a question mark written in ancient starlight. This stellar stream is a ghost of a past victim, but another galaxy is fighting a different fate, one of violent expulsion. Streaking through the heart of the Leo cluster is a galaxy moving at a velocity so extreme it defies the very idea of gravitational community. While most members orbit the cluster's core in a stately, bound dance, this one is a runaway, its speed so great that it appears to be on a one-way trip to intergalactic space. It is a high-velocity ejector, a celestial projectile fired from the cluster's deepest gravitational well. How does a galaxy weighing hundreds of billions of solar masses get catapulted like a pebble from a slingshot? The most likely culprit is a devastating gravitational encounter. Picture not a simple collision, but a complex, three-body gravitational dance near the cluster's dense core. Imagine this galaxy in its orbit, passing perilously close to a binary system of two other massive galaxies, or perhaps a tight pairing of a giant galaxy and the cluster's central dark matter potential. As it swings through this chaotic gravity field, it can steal orbital energy from the other bodies in a process called a gravitational slingshot. The result is a tremendous boost in speed, flinging the galaxy outward on a hyperbolic trajectory that may never bring it back. It is the cosmic equivalent of a spacecraft using a planet's gravity to gain velocity, but on a scale of almost unimaginable power. The implications of such an event ripple through our understanding of the cluster's history. For a galaxy to be ejected, an immense amount of kinetic energy had to be injected into the system. This energy comes from the gravitational binding energy of the cluster itself, subtly altering the orbits of every other member. Finding such a high-velocity object is like finding a smoking gun, evidence of a particularly violent and dynamic past interaction that likely occurred hundreds of millions of years ago. Its trajectory is a frozen record of that ancient catastrophe. What becomes of such an exile? If it truly escapes the cluster's gravitational grasp, its fate is a lonely one. It will journey through the cosmic voids as a field galaxy, stripped of the dense environment that once surrounded it. Its star formation may sputter out as it loses any remaining reservoir of intergalactic gas to ram pressure, and it will evolve in profound isolation. Yet, its very existence forces us to reconsider the energy balance within clusters. These structures are not serene islands, they are dynamic battlegrounds where galaxies can be both created and destroyed, and sometimes violently evicted. This single, speeding dot of light is a testament to the raw, chaotic forces that continue to sculpt the universe on the grandest scales. A sudden, silent flash of light erupted from a dense crowd of ancient stars. Orbiting one of the Leo cluster's giant galaxies is a globular cluster, a spherical swarm of millions of stars bound together by gravity. Within that crowded city of suns, something brilliant and violent happened. Telescopes monitoring the region captured a pinpoint of light that brightened dramatically over a few days, then just as mysteriously faded away into the background glow. It was a transient optical event, a cosmic flare that announced its presence and then vanished before we could truly understand it. The data was definitive in its scarcity, a brief spike on a light curve chart, a ghost in the machine of the night sky. The frustration for astronomers is palpable. They caught the event, but the evidence was gone almost as soon as it arrived, leaving behind only a gallery of possible suspects, each more dramatic than the last. The first possibility is a stellar merger, a catastrophic dance of destruction. In the cramped core of a globular cluster, stars can pass perilously close. Two aging stars, perhaps white dwarfs, could have finally spiraled into each other, triggering a titanic thermonuclear blast that outshone the entire cluster for a brief, glorious moment. Another explanation is microlensing, a chance alignment where a faint foreground object, maybe a dim star or even a rogue planet, passed directly in front of a background star in the cluster. Its gravity would have acted as a natural magnifying glass, amplifying the distant star's light into a temporary spike before fading as the alignment shifted. It could also have been a classical nova, a thermonuclear explosion on the surface of a white dwarf stealing gas from a companion star. Yet the most tantalizing and unsettling possibility involves a hidden predator. Globular clusters are suspected to harbor intermediate mass black holes, monsters with the mass of hundreds or thousands of suns, bridging the gap between stellar corpses and the supermassive giants in galactic centers. If such a black hole lurked in this cluster, a star that wandered too close could have been tidally disrupted, violently shredded and pulled into a glowing accretion disk, creating a brilliant flare of light as its material was consumed. The event faded before spectroscopic observations could hunt for the chemical signatures that would confirm any one of these scenarios. This is the heartbreak of transient astronomy, the race against time where the universe reveals a secret and then instantly hides it again. The only recourse is relentless vigilance. Astronomers continue to monitor this globular cluster and thousands like it, using automated surveys that scan the skies night after night, hoping to catch another flash. When they do, they will mobilize telescopes around the world and in space within minutes, aiming to capture every wavelength of light from the event's birth to its death. Visualizing it is a study in cosmic ambiguity, time-lapse imagery showing a single point among thousands flaring to life and then sinking back into obscurity, while artist concepts depict the violent possibilities, from colliding suns to a star being stretched into a brilliant stream of plasma by an unseen gravitational monster. That one brief flash is a message in a bottle cast into the void from a crowded stellar metropolis. We read the note, but the handwriting is blurred, the language unknown. It reminds us that for every mystery we solve in the cosmos, a dozen more flicker and vanish before we can even ask the right questions. The faint radio glow and searing X-rays are not the only forces shaping the cluster's invisible atmosphere. Woven through that million-degree plasma is a hidden architecture of immense power, a vast, invisible web of magnetic fields, stretching across the entire Leo cluster for millions of light-years. This coronal magnetic field is a ghostly skeleton that holds profound influence, yet its very existence is a deep cosmological puzzle. We cannot see magnetism directly, but we can detect its fingerprint. When radio waves from distant galaxies or from the cluster's own relics pass through this magnetized corona, their polarization, the orientation of their waves, is subtly twisted. It is like looking at the world through a slowly rotating lens of pure force. These delicate measurements reveal a field that is surprisingly strong and coherent on scales that defy easy explanation. How does a magnetic field, which we typically associate with stars and planets, come to span an entire galaxy cluster? The leading theories point to origins in the deep past. One idea suggests these are primordial seed fields, incredibly weak magnetic imprints from the universe's infancy that were stretched and amplified to their current strength as the cluster itself formed and grew. Another, more dynamic theory invokes a cosmic dynamo. As galaxies move and merge within the cluster, they stir the hot gas into a roiling, turbulent frenzy. This motion, acting like a gigantic engine, could theoretically twist and amplify any weak initial fields into the organized structures we detect. The problem is scale and time. Our best simulations struggle to generate fields this strong and widespread through turbulence alone within the age of the universe. It is akin to trying to magnetize an ocean by stirring it with a spoon. The process seems too slow, too inefficient for the result we observe. This leaves open more exotic possibilities, like the injection of magnetized plasma from the furious jets of supermassive black holes over billions of years, painting the void with magnetic lines like cosmic graffiti artists. Regardless of its origin, this magnetic web is not a passive decoration. It fundamentally shapes the cluster's behavior. These fields guide and confine the ultra-relativistic particles that create radio relics, focusing their emission into sharp arcs. They provide pressure that supports the hot gas against gravity, subtly altering how it flows and cools. They even affect how heat is transported through the corona, potentially solving some of the fine-tuning mysteries of the cool core. Most crucially, these fields are the unseen tracks for cosmic accelerators. When shock waves from ancient mergers rip through the cluster, particles are not just accelerated by the shock itself. They surf along these magnetic field lines, gaining tremendous energy to produce the brilliant radio and X-ray emissions we study. This means that to truly understand any of the violent phenomena we have discussed, from the ghostly relics to the puzzling cavities, we must first map this invisible magnetic lattice. Visualizing it requires a blend of art and supercomputer science, with animations showing faint blue lines of force emerging from swirling galaxies, stretching and tangling across the void, shaping the paths of glowing particles in a silent, enduring dance of power. The coronal magnetic field is the cluster's central nervous system, a fossilized record of every merger, every jet, every stir in its long history, written in a language of force we are only beginning to translate. The cosmic scales we use to weigh the universe have just tipped, revealing a profound imbalance. Deep within the Leo cluster, the invisible anchor of dark matter is not where it should be. Meticulous studies combining gravitational lensing, galaxy motions, and X-ray gas maps have uncovered a startling fact. The cluster's true center of mass is significantly offset from the brightest concentration of galaxies and the peak of the hot, glowing gas. The dark matter halo, the gravitational bedrock of the entire structure, is lopsided. Imagine a spinning top where the heaviest weight is not in the middle but glued to one side. It still spins, but with a wobble that betrays its uneven core. That is the Leo cluster. This asymmetry is a direct challenge to our assumption that massive clusters are relaxed, symmetrical systems where all components, stars, gas, and dark matter, have settled into a smooth, balanced equilibrium after billions of years of evolution. Such a pronounced offset should not persist for long in cosmic terms. Gravity is a relentless force that seeks to smooth out irregularities. The fact that we see this skew today means we are likely catching the cluster in a rare, dynamic state, mere moments after a cosmic car crash. The leading explanation is a recent off-axis merger. Picture not a head-on collision, but a glancing blow where a smaller group or cluster plowed into the Leo cluster's outskirts at an angle. In the aftermath, the dark matter halos of the two systems, which interact almost solely through gravity, have begun to overlap and merge, but the visible components, the galaxies and the hot gas, behave differently. The galaxies, like swarms of bees, largely pass through each other unscathed. The hot gas, however, is a fluid. It experiences a drag and gets slowed, heated, and displaced by the collision. This creates a lag, a disconnect. The dark matter, driven by gravity alone, has already shifted toward the combined center of mass of the merger. The X-ray gas, still sloshing and settling from the impact, has not yet caught up. The brightest galaxies might also be trailing behind, caught in the gravitational wake. We are seeing a snapshot of a cosmic realignment in progress, a unique window into how these colossal structures assemble themselves. Measuring this asymmetry is a monumental challenge. It requires piecing together multiple, imperfect maps of reality. Weak gravitational lensing provides a statistical map of the total mass distribution, but it is blurry. The motions of hundreds of galaxies give clues to the gravitational potential, but their orbits are complex. The X-ray glow pinpoints where the hot gas is densest. Only by overlaying all these datasets can the offset be revealed, and even then, it requires exquisite precision and a willingness to question the expected symmetrical models. This lopsidedness has profound implications. Astronomers use massive clusters as cosmic yardsticks, assuming they are regular, relaxed objects to measure the expansion history of the universe and the nature of dark energy. If a significant number of clusters are still recovering from recent mergers and are not in equilibrium, our measurements with them could contain subtle, systematic errors. The Leo cluster's wobble is a cautionary tale, reminding us that the cosmos is not a static museum display but a construction site, full of half-finished projects and recent collisions. Visualizing this would show a stunning mismatch, a contour map of mass in deep purple, its heart shifted to one side, while the brilliant white glow of galaxies and the fiery red cloud of X-ray gas remain huddled together, displaced from the true gravitational center. It is a portrait of cosmic disorder, a silent testament to a violence so recent that the universe has not yet had time to clean up the evidence. Even the cold, dark spaces between galaxies are not truly empty. A faint, pervasive warmth glows across the Leo cluster in the infrared, a subtle heat signature that our eyes cannot see but space telescopes like Spitzer and Herschel have clearly mapped. This diffuse infrared emission blankets the region, a soft, cosmic background hum that should not exist. When astronomers add up all the known sources of infrared light, the combined glow of countless cool stars and the gentle warmth of interstellar dust grains within every galaxy, they come up short. A significant portion of the cluster's infrared energy budget is simply unaccounted for, a persistent excess that points to something hidden. This unidentified infrared emission is a ghost in the thermal spectrum. One leading suspect is a population of extremely cold dust grains, not safely tucked inside galaxies, but drifting freely in the intracluster medium itself. This would be dust so frigid, only a few degrees above absolute zero, that it emits almost exclusively in the far infrared and submillimeter wavelengths. But the origin of such dust is a puzzle in itself. How could delicate grains, typically formed in the atmospheres of dying stars within galaxies, be expelled and survive in the harsh, hot plasma between them? Another possibility points to exotic, large molecules known as polycyclic aromatic hydrocarbons, which can produce a distinctive set of infrared emission bands. Yet the spectrum of the excess glow does not perfectly match these known fingerprints. The most speculative and thrilling idea ventures into the realm of particle physics. Could this faint infrared bath be a sign of decaying dark matter? Some theoretical models propose that certain hypothetical dark matter particles, like actions or sterile neutrinos, could decay slowly over cosmic time, releasing photons in the infrared range. If true, this diffuse glow would be our first direct glimpse of dark matter's nature, not through its gravity but through its light. For now, the emission remains an enigma. Its distribution is too smooth and widespread to be easily linked to any single galaxy or recent event. Visualizing it requires shifting our vision to the infrared, where the familiar points of starlight fade, and the entire cluster is immersed in a faint, patchy aura of unexplained warmth, highlighted in contrasting reds and oranges against the dark. This quiet, thermal mystery reminds us that even in the absence of brilliant explosions or violent collisions, the universe hums with energies we have not yet learned to name, a background whisper of heat that holds secrets about everything from cosmic dust to the fabric of reality itself. This galactic contradiction is written in the very motion of its stars and gas. Within the Leo cluster, a specific spiral galaxy presents a dizzying spectacle, one where its inner heart and outer body spin in opposite directions. Detailed kinematic maps, which chart the velocity of every component, reveal a startling split. The dense central bulge of stars rotates serenely in one direction, while the vast, gaseous disk that surrounds it whirls in the exact opposite way. It is a cosmic waltz where the partners are moving against the music, a configuration so rare and unstable it defies our expectations of galactic harmony. How does a galaxy end up with such a profound internal conflict? The leading theory points to a violent act of cosmic consumption. Billions of years ago, this spiral likely had a more uniform rotation. Then it encountered an immense cloud of primordial gas, or perhaps a small, gas-rich dwarf galaxy that was orbiting the cluster in the opposite direction. Through a slow, gravitational embrace, the spiral captured this external material. Because the captured gas possessed its own opposite angular momentum, it did not simply merge into the existing disk. Instead, as it settled, it formed a new counter-rotating layer on the outside, like a second record spinning backwards on the same turntable. The process of how this settles into a stable, long-lived configuration is the core of the mystery. Our computer simulations struggle to recreate it without the galaxy tearing itself apart through internal friction, or the two components violently cancelling each other out. The fact that we see such a galaxy at all, especially in the turbulent environment of a cluster, suggests the accretion event must have been remarkably gentle and the settling process incredibly slow, allowing the two opposing flows to reach a precarious truce. Visualizing this requires a shift from static images to motion. First, a kinematic map would show the galaxy split in two by color, with red arrows in the core pointing one way and blue arrows in the outer disk pointing the opposite direction, a stark visual divorce of motion. Then, an animation would bring the theory to life, showing the host galaxy spinning calmly before a faint, counter-orbiting cloud of gas slowly spirals in, drawn by gravity, and eventually paints a new, backwards rotating disk over the old one. This galaxy is not just an oddity, it is a fossilized record of a specific, messy meal. Its existence tells us that galaxies do not grow neatly. They are built through a history of collisions and captures, sometimes acquiring material that fundamentally contradicts their original nature. That this contradictory state can persist for eons is a quiet marvel, a testament to the complex and often contradictory forces that sculpt every island of stars in the dark. At the very heart of the Leo cluster, a gravitational monarch reigns, but its crown is curiously heavy. The central dominant galaxy, a colossal elliptical, is an imposing giant, its starlight alone speaking of immense mass. Yet this stellar might is creating a cosmic paradox. When astronomers use the motions of its stars to weigh it, and then compare that weight to the total gravitational pull of the entire cluster as measured by other methods, the numbers do not align. This galaxy seems to be too massive for its kingdom. It breaks a fundamental scaling relation, a rule of thumb that says the brightest, most massive galaxy in a cluster should have a predictable relationship to the cluster's total mass. Here, that rule is shattered. To understand the depth of this discrepancy, we must look at the different scales we use. The stellar dynamics method is like taking a census of a city and estimating its wealth by watching how fast the citizens move within it. The faster the average motion, the stronger the gravitational pull holding them in, and thus the greater the total mass of the city itself. By this measure, the central galaxy is extraordinarily wealthy, packed with stars in a deep gravitational well. But then we step back and measure the wealth of the entire country, the cluster. We do this by two other independent methods. Gravitational lensing maps the total mass, including all the dark matter, by how it bends light from distant galaxies. The temperature and pressure of the X-ray emitting hot gas also acts as a barometer for the cluster's total gravitational depth. Both of these larger scale measurements agree with each other, painting a consistent picture of the cluster's overall mass. Yet when we subtract the mass of all the other galaxies and the hot gas, the portion that should belong to the central galaxy according to the scaling relation is significantly smaller than what the stellar motions inside it insist is there. It is as if a single skyscraper, by all internal accounts, weighs as much as a dozen city blocks, but the city's overall budget only has room for one. This forces a difficult choice between several unsettling explanations. Perhaps our understanding of how stars move in such dense environments is flawed. Maybe the stellar initial mass function, the blueprint for how many big versus small stars are born, was radically different in this galaxy's extreme past, leading us to misjudge its true mass from its light. Or the dark matter within this particular galaxy could be distributed in a bizarre, ultra-concentrated way, a spike of invisible mass that boosts the star's speeds without contributing proportionately to the larger-scale lensing signal. Each possibility challenges a different pillar of astrophysics. Visuals would starkly contrast this imposing golden-white galaxy against graphs where its data point lies far off the expected curve, a lonely outlier defying a universal trend. This is not a minor accounting error. It is a fundamental question about how the mightiest galaxies grow at the hearts of the greatest structures in the universe. Does this monarch truly possess a hidden, disproportionate treasure, or are our scales for weighing cosmic kingdoms somehow broken? This final mystery is written in the most violent language the universe speaks. A faint, persistent glow of gamma rays, the most energetic form of light, emanates from the direction of the Leo cluster. Detected by instruments like the Fermi Gamma Ray Space Telescope, this diffuse signal is not a single flash but a steady, ominous hum. Its very existence is a high-energy riddle, a whisper of processes so powerful they bridge the gap between the smallest particles and the largest cosmic structures. Distinguishing its true source is a monumental challenge as it sits at the ragged edge of our detection capabilities, a ghost in the gamma-ray sky. The first and most conventional explanation points to the cluster's own seething atmosphere. The space between those galaxies is filled with that hot, thin plasma and crisscrossed by magnetic fields. It is also likely flooded with cosmic rays, protons and atomic nuclei accelerated to nearly the speed of light by shock waves from ancient mergers or the jets of active black holes. If these ultra-fast particles collide with the slow-moving protons in the intracluster gas, the smash can produce pions, unstable particles that decay almost instantly into gamma rays. This process would paint the entire cluster with a faint, uniform glow, a byproduct of the violent weather within its borders. It is a plausible astrophysical answer, but one that requires the cluster to be a surprisingly efficient and long-lived cosmic ray accelerator. A second, more speculative possibility ignites the imagination of particle physicists. This faint glow could be the long-sought signature of dark matter annihilation. Theories suggest that dark matter particles, wherever they are densely packed, might occasionally collide and annihilate each other, converting their mass directly into energy and producing a spray of standard particles, including gamma rays. The dense, massive halo of the Leo cluster would be one of the best places in the nearby universe to look for such a signal. If this glow is indeed from dark matter, it would be a revolutionary discovery, our first direct detection of the invisible stuff that shapes the cosmos, not through its gravity but through its self-destruction. Visualizing this would show diagrams of theoretical dark matter particles colliding within the cluster's vast halo, erupting into cascades of light, their gamma-ray signature superimposed on a Fermi sky map. Yet a third option brings us back to known celestial engines. The glow might not be truly diffuse at all, but the combined, unresolved flicker of hundreds of active galactic nuclei, the supermassive black holes at the hearts of galaxies that are actively feeding. Each one is a brilliant point source of gamma rays. At the distance of the Leo cluster, the faintest of these could blur together into a single, hazy patch of light in our telescopes, mimicking a smooth, extended glow. Teasing apart this pointillist painting from a true, smooth emission is a task of exquisite difficulty, requiring sensitivities beyond our current instruments. This persistent gamma-ray glow is therefore a frontier. It represents the outermost limit of our observational reach, where the known astrophysics of cosmic rays, the hidden physics of dark matter, and the unresolved chatter of black holes all converge into a single, ambiguous signal. Future telescopes with finer angular resolution and greater sensitivity will one day dissect this light. They will either reveal a population of faint, twinkling black holes, map the fury of cosmic rays on a universal scale, or just possibly unveil the first light from the dark universe itself. It is a fitting final note for the Leo cluster's symphony of mysteries, a high-energy question mark hanging in the void, reminding us that the greatest puzzles often shine in the light we are only beginning to see. 25 cosmic enigmas stand before us, a testament to a universe that refuses to be simple. From the ghostly Leo ring to the silent scream of gamma rays, every unexplained phenomenon in this distant cluster is a crack in the facade of our understanding. These are not minor curiosities, they are fundamental challenges. Each one, from the missing dwarfs to the lopsided dark matter, forces us to question the very pillars of modern astronomy, our models of dark matter, our narratives of galactic life and death, and even our grasp of gravity itself. The Leo cluster is more than a collection of galaxies. It is a cosmic laboratory, a natural experiment on a scale we could never recreate, showing us where our theories break down. And that is the true value of these mysteries. They are not failures of science, but its fuel. Every phantom galaxy, every contradictory spin, every unexplained glow is a signpost pointing toward a deeper truth we have not yet grasped. They remind us that the cosmos is far stranger, more dynamic, and more wonderfully complex than we have dared to imagine. If this journey through cosmic detective work has sparked your curiosity, hit that like button. Subscribe for more deep dives into the universe's greatest unsolved puzzles, and let us know in the comments below which Leo cluster phenomenon do you think is the most mind-bending of all. Until our next exploration, keep looking up. The greatest mysteries are still waiting.